Hello everyone, here is Khaled Omar, and in this video I'm going to demonstrate Chapter 2 of the CCNA 200-301 Volume 1, which is Fundamentals of Ethernet LANs. So let's think about the enterprise computer networks. There are two types of networks. We can classify the enterprise's computer networks into two types of technology. The first one is the local area networks or LANs. The second one is wide area networks or WANs. Let's define the LANs and WANs. First of all, let me bring the pen. So to define LANs, it is typically used to connect nearby devices. So each device in the same room, in the same building, or in the campus of buildings, and they can connect to each others. This form LANs. There is another type of networks or enterprise networks called WANs, and it is typically used to connect devices that are relatively far apart. There is big distances between the network components. Or if you have a LAN here, LAN 1 and LAN 2, and they are far from each others, you can use service provider WAN network to connect your LANs. So this is LAN 2 and this is LAN 1. So together, LANs and WANs create a complete enterprise computer network, working together to do the job of a computer network, delivering data from one device to another. So just think about the two enterprise networks as simply as LANs and WANs. LANs between connect nearby devices, and WANs connect devices that are relatively far apart. So let's give an overview of the local area networks. We will start by LANs, and then we will discuss WANs in a later video. So many types of LANs have existed over years, but today's networks use two general types of LANs. Ethernet LANs, and it is defined in the IEEE 802.3, and sometimes we call it wired LANs. And the second type is wireless LANs, or IEEE 802.11. This is the standard from the IEEE. So Ethernet LANs happens to use cables for links between nodes. Sometimes we use nodes or hosts. So hosts, sometimes we call it nodes. And because many types of cables use copper wires, Ethernet LANs are often called wired LANs. So if you will think about the types of LANs, we have wired LANs and wireless LANs. The wired LAN uses cables, usually copper wires or fiber optic cables, and the wireless uses the electromagnetic field through the air. So we have Ethernet LANs also make use of fiber optic cabling. So we have here copper wires or fiber optic cables, which includes a fiberglass cord that devices uses to send data using light. If you will use copper wires, you use electrons. If you will use fiber optic cable, you use light inside the fiber optic cables. The wireless LANs does not use wires or cables, instead using radio waves for the links between nodes. So wireless LANs does not use any type of cabling, whether it is copper wires or fiber optic cable. Instead, it uses the radio waves through the air. So let's define what is Ethernet. Ethernet actually refers to a family of LAN standards that together define the physical and data link layers of the world's most popular wired LAN technology. So these standards, defined by the Institute of Electrical and Electronics Engineers, or IEEE, define the cabling, the connectors on the end of the cables, and also the protocol rules and everything else required to create an Ethernet LAN. So the organization that is responsible for issuing the standards for Ethernet is called IEEE, or the Institute of Electrical and Electronics Engineers. It defines everything, the cabling, the connectors, the protocols, everything in the Ethernet network or Ethernet LAN. Let's give a simple example of a typical small office, home office LAN. So here we have Ethernet switch, Ethernet cable or cables, Ethernet ports on the switch, and some PCs, 3 PCs in this figure, and a router and a printer. So simply to make a small office, home office local area network, you just need a simple switch and connect hosts or nodes to this switch through Ethernet cables. The switch is called Ethernet switch, and the cables are called Ethernet cables because here we are using LANs or Ethernet LANs, but in a small office, home office network. We are not using wireless LANs in this scenario. So it is simple like that. Have a switch, hook up the PCs and the printer, and connect it to the router, and the router is connected to the internet. Although the figure shows the switch and routers as separate devices, many small office, home office Ethernet LANs today combine the router and the switch into a single device. As you can see here, this is perform switching and routing. So it is called a network device, or we call it a router. Sometimes we call it router. So these devices typically have router on the packaging, but many models also have 4 ports or 8 ports Ethernet LAN switch ports built into the device. So this device from inside consists of a switch connected to a router, and they are in the same device. And typical small office, home office LANs today also support wireless LAN connections. So using these access points, these antennas connected to the device. So we have here antennas. It supports wireless LANs. So we here laptops or smartphones can connect to the network. So you can build a single small office, home office LAN that includes both Ethernet LAN technology as well as wireless LAN technology, which is also defined by the IEEE, as we mentioned in in one of the slides, that the Ethernet LAN IEEE 802.3 and the wireless LAN technology defined by IEEE 802.11. So wireless LANs defined by the IEEE using standards that begin with 802.11 use radio waves to send the bits from one node to the next. So most wireless LANs rely on networking device, which is called wireless LAN access point. So when you hear about wireless LAN access point, think about the wireless LAN standard IEEE 802.11. And there are multiple of standards, such as 802.11a, b, g, n, ac, and so on. The access point acts somewhat like an Ethernet switch, in that all the wireless LAN nodes communicate with the wireless access point. As you can see here in this figure, we have here some tablets that are connected through the radio waves to the access point, and the access point is connected to the switch. And as we mentioned, some devices have all these three devices in the same device: the switch, the Ethernet switch, the access point, and the router. So if the network uses an access point, that is a separate physical device in this scenario. But in the previous slide, it was included in the device which we called a router for the purposes of this demonstration. Sometimes some people have modems or call it modems in case you are connecting through the ADSL to the internet. So the access point then needs a single Ethernet link to connect the access point to the Ethernet LAN. So simply, if you want to use the wireless standard, you bring an access point connected to the switch, and then devices, wireless devices such as tablets, such as laptops, smartphones, can connect to the access point and then connect to the network and be able to communicate with the PC or the printer to print or connect to the internet. So there is also, instead of small office, home office, we have another type of LANs that is called enterprise LANs, which is different than the small office, home office network, but it has some similarities, but it is for large scale. So in this figure, we have here 3 floors in a building: first floor, second floor, and third floor. The first floor has an Ethernet switch that's connected to the hosts PC1 and tablet 1 through the access point, and each floor has the same Ethernet switch and an access point and some nodes connected to the Ethernet LAN. But in enterprises, to connect these switches together, we use a switch called distribution switch that collects all the Ethernet access switches through one or more cables, and we will demonstrate later why we use more than one cable. And for this demonstration, we just need to understand that access switches in each floor can be gathered together through a distribution switch and then connect to a router and then to the rest of the enterprise network. After you do this, all these hosts in each floor, the PC and the tablet, can communicate with the PC and tablet in the second floor, and similarly in the first floor. So they are all in the same network, so they can communicate to each others. So really there are a variety of Ethernet physical layer standards. We will discuss here in this slide the first layer in the TCP/IP, which we called the physical layer or layer 1. There are a variety of standards. The term Ethernet refers to an entire family of standards It is not one type of standard, it is a family of standards. Some standards define the specifics of how to send data over a particular type of cabling and at a particular speed. So it defines the type of cabling and the speed. Other standards define protocols or rules that the Ethernet nodes must follow to be a part of an Ethernet LAN. All these Ethernet standards come from the IEEE, as we mentioned, and include the number 802.3 as the beginning part of the standard name. And later we will see a lot of these standards in a table so we can identify each one of them. Devices using UTP cabling, so this is one kind of cabling, transmit data over electrical circuits via the copper wires inside the cable. Fiber optic cabling, the more expensive alternative, allows Ethernet nodes to send light over glass fibers in the center of the cable. So we have standards that define the cabling. So we have here UTP cabling, and there is also we have STP cabling as copper wires, and we have another standard that defines the fiber optic cabling as an alternative to the UTP cabling or STP cabling, or in general the copper wires. So the IEEE defines Ethernet physical layer standards using a couple of naming conventions. So these naming conventions are the formal IEEE name, which begins with 802.3, followed by some suffix letters, and the informal IEEE name identifies the speed as well as a clue about whether the cabling is copper or fiber. So we have here a list of examples of types of Ethernet. If the standard will start with 802, this is the formal IEEE name. If it will start by speed, this is the informal IEEE standard name. Let's take, for example, the 100 megabit per second speed, or sometimes we call it fast Ethernet. The informal IEEE standard name for fast Ethernet is 100 base T, and T refers to copper, and 100 refers to the speed. Let's take 1000 megabit per second or 1 gigabit per second. It is called Gigabit Ethernet, and the informal name is 1000 base LX, and LX here uses fiber optic cabling and speed 1 gigabit per second, and the formal IEEE standard name is 802.3Z. For fast Ethernet, the formal IEEE standard name is 802.3U. Let's take 10 gigabit per second or 10 giga Ethernet. It uses informal name 10 giga base T, and once you say T, it means copper wire. If you see LX, it is fiber optic cabling. The formal IEEE standard name is 802.3 AN, and here tells you the maximum cable length 100 meter, and for 100 megabit per second or 100 base T, it is 100 meter using copper wires. When we use fiber, the maximum length is 5 kilometer, and so on. So all just you need to know from this slide the formal IEEE standard name and the informal IEEE standard name, and which standard, what is the speed of each standard and the type of cabling. So when we build Ethernet, physical Ethernet LANs with STP or UTP, there is two types of UTP of cabling of using copper wires. We have UTP or unshielded twisted pair and shielded twisted pair cable. So we have shielded and unshielded. And shielded, that is, has this shield around the pair of wires. So before the Ethernet network as a whole can send Ethernet frames between user devices, each node must be ready and able to send data over an individual physical link. And here is a note: in a UTP cable, the wires will be twisted together instead of being parallel. As you can see here, each pair has two wires twisted, not in parallel. Why? The reason why is to help cancel out most of the electromagnetic interference. So most networking physical links that use copper wires use twisted pair. Why? If you have a wire here that has electrical signal passing through it, it makes an electromagnetic field in this direction. The other wire has also electrical signal passing through it, so the electromagnetic field direction will be in this direction, and because of they have the same value, the electromagnetic field will be neglected or will remove each others because they are equal values in two opposite directions. That's why we use twisted pairs to prevent or to cancel the electromagnetic interference. So let's discuss transmitting data using twisted pair. First, to create one electrical circuit, Ethernet defines how to use two wires inside a single twisted pair of wires. As you can see in the figure, we have here transmitter and receiver. One wire from the pair is connected to the transmitter, and the other side is connected to the receiver. So the two wires or the pair of wire can has electrical signal or electrical current passing through the cables, and they can go in this direction. The figure doesn't show a UTP cable between two nodes, but instead show how individual wires that are inside the UTP cable. An electrical circuit requires a complete loop, as you can see here. This is called a complete loop. So the two nodes using circuitry on their Ethernet ports connect the wires in one pair to complete a loop. And after the loop is complete, electricity will flow. So in this slide, we are going to define what is Ethernet link. Actually, if an Ethernet link refers to any physical cable between two Ethernet nodes. Think about it like that. Any physical cable, whether it is copper wire or fiber optic cable, between two Ethernet nodes. And these nodes can be between two PCs, between two switches, between PC and switch, and so on. So we have here RJ45 port, whether it is for a PC or a NIC card in a PC. I mean a port in a PC or a switch is connected to another RJ45 port. We call this port RJ45, whether it is a switch port or a PC port. and this is the NIC card that is implemented in the PC. So this port is here on the switches. We have here a switch with 5 ports, and these are the connectors of the cable, RJ45 connectors, and this is the patch cord of a UTP cable that is used to connect between two nodes, whether two PCs, two switches, a PC and switch, access point or switch, to switch. So the 10 base T and 100 base T standards requires 2 pair of wires, while the 1000 base T standard requires 4 pairs, and 4 pairs means 8 wires, and 2 pairs is 4 wires. Each wire has a color-coded plastic coating. We have here green, solid green, and striped green, and blue, orange, and brown. Each wire has a color-coded plastic coating, with the wires in a pair having a color scheme. As we mentioned here, for green we have solid green and striped green. For orange the same, for blue the same, and for brown also the same. Striped and solid. For example, for the green wire pair, one wire's coating is all green or solid green, while the other wire's coating is green and white striped. As you can see here, this is green striped. Many Ethernet UTP cables use an RJ45 connector on both ends. As you can see here, these are the RJ45 connectors that is connected on both ends of a UTP or STP cable. So the RJ45 connector has 8 physical locations. Inside, those are 8. 1, 2, 3, 4, 5, 6, 7, 8. Into which 8 wires or 4 pairs in the cable can be inserted, called pin positions, or simply pins. These are called pins. So the RJ45 connector has 8 pins. These pins create a place where the ends of the copper wires can touch the electronics inside the nodes at the end of the physical link so that electricity can flow. And to complete the physical link, the nodes each need an RJ45 Ethernet port, because here we have UTP cable with RJ45 connectors, and we need to complete the link. The physical link consists of a cable that is connected to 2 nodes. Let's, for example, connect the cable to this RJ45 switch port, and the other side is connected to a PC with NIC card or network interface card with RJ45 port. This will complete the link. So the nodes each need an RJ45 Ethernet port that matches the RJ45 connectors on the cable, so that the connectors on the ends of the cable can connect to each node. So we will have here a PC with network interface card like this one. We call it Ethernet network interface card with RJ45 port, and here we have a switch with 5 or 4, let's say 4 Ethernet ports, RJ45 ports, and we have this cable, or we call it patch cord, RJ45 with RJ45 connectors. We will use the cable to connect these two nodes. Here is the RJ45 connector, and here is the RJ45 connector, and this will complete the physical link. PCs often include this RJ45 Ethernet port as part of a network interface card, which can be an expansion card on the PC, or it can be built in the system itself. Sometimes you purchase a PC with built-in network interface card or an expansion card like this one. This is an expansion card. This slot is implemented in the motherboard, and it can be used for networking as a network interface card. And of course, it's an Ethernet network interface card. If you have a laptop, it has two types of cards, wired and wireless. You can use the laptop here for wired using its RJ45 port instead of this PC. So to give its customers flexibility as to the type of links, Ethernet links, actually this is Cisco. Cisco gives its customer flexibility to the types of Ethernet links. Even after the customer has bought the switch, Cisco switches include some physical ports whose port hardware, the transceiver, can be changed later, such as these ports. These ports can be used for copper wires or fiber optic cabling. So these 12 ports can be used for copper wires, and these two ports can be used for either copper wires or fiber optic cables based on the type of the small form factor pluggable you are purchasing to hook it up inside these ports. So sometimes you use it as here for Ethernet RJ45 cable, or you can use it a different one for fiber optic cable. So in this case, the figure shows an enhanced small form factor pluggable, or SFP plus transceiver, which runs at 10 gigabit per second. The old one we called it Gigabit, and the newer one we call it small form factor pluggable. And as you can see, this one, the SFP, is smaller than the Gigabit, but they are used for the same purpose. So Gigabit Ethernet Interface Converter, or Gigabit, the original form factor for a removable transceiver for gigabit interfaces. This can be inserted in the SFP ports, and you can use RJ45 connector with, of course, cable, and otherwise you can use another Gigabit for fiber connector, and we will mention later what are the types of connectors that are used with fiber cables. Then small form pluggable SFP, the replacement for Gigabits, used on Giga interfaces with a smaller size, taking less space on the side of the networking card or switch. So when you purchase, for example, a Cisco switch, you find some ports that are used dedicated for RJ45 ports, and some other ports that can be used either for Ethernet wired cables, copper wires, or fiber optic cables. It is removable. These Gigabits or SFPs are removable, and you can change based on your requirement. The last one is a small form pluggable plus, same size as the SFP, but used on 10 gigabit per second interfaces. So sometimes the port is not compatible with the JBIC. Sometimes it uses only SFP. Of course, it has a smaller size. So be careful when you choose your JBICs for these types of connections, whether it is JBIC or SFP. There is something called UTP or STP cabling pin outs for 10 base T and 100 base T. This is Ethernet and this is fast Ethernet. This uses speed, Ethernet uses speed 10 megabit per second, and the fast Ethernet uses 100 megabit per second, and T means copper wires. So that's why we said here UTP or STP cabling pin outs. Ethernet network interface card transmitters use the pair connected to pins 1 and 2 for transmitting, and the network interface card receivers use a pair of wires at pin position 3 and 6. So if you have here a network interface card with an RJ45 port, it has 8 pins. Let's say here 1, 2, 3, 4, 5, 6, 7, 8. Pin number 1 and pin number 2 is used for transmitting, and pin number 3 and pin number 6 used for receiving. LAN switches, knowing those facts about what Ethernet NICs do, so it does the opposite. The receivers use the wire pairs at pins 1 and 2, and the transmitters use the wire pair at pins 3 and 6. So LAN switches is opposite than the Ethernet network interface cards. For switches, if you have RJ45 port here, and it uses 1 and 2 for receiving and 3 and 6 for transmitting. So to allow a PC network interface card to communicate with a switch, the UTP cable must use a straight-through cable pin out. And we will know how to do the straight-through cable pin out in another coming slide. But to allow a switch to communicate with a switch or a PC to a PC, the UTP cable must use a crossover cable pin out, because all what you want to do is to connect the transmitter to the receiver on the other side, and the transmitter here to the receiver in this side. So if you are using switch to switch, then pin 1 and 2 should be connected to pin 3 and 6 on the other side, which is called crossover cable. But if you are going to connect a PC to a switch, the PC uses 1 and 2 for transmitting and 3 and 6 for receiving. And the LAN switch uses 1 and 2 for transmitting, for receiving, and 3 and 6 for transmitting. So you will connect 1 and 2 to 1 and 2, and 3 and 6 to 3 and 6 in case of connecting an Ethernet, a PC to an Ethernet LAN switch. And here are the standards that we are using when connecting straight through cable pin out. First of all, to define the word pin out, it refers to the wiring of which color wire is placed in each of the 8 numbered pin positions in the RJ45 connector. Which color will be used inside the connector is called pin out. So for a straight through cable pin out, we have two standards, T568A and T568B. And they are the same. One here is connected to one here. Two here is connected to two here, and so on. But the difference is that T568A uses 1 and 2 for green and 3 and 6 for orange. But T568B uses 1 and 2 for orange and 3 and 6 for green. But you need to connect green to green and orange to orange to have a straight through cable. So in this standard, 1 to 1, 2 to 2, 3 to 3, 4 to 4, and so on until 8 to 8. And in the other standard, T568B, 1 and 1 to 1, 2 and to 2, 3 to 3, and so on until 8 to 8. But the difference is in the 1 and 2 colors and 3 and 6 colors. So here we have a PC with a network interface card connected to a switch. As we mentioned, the type of cable will be straight through because the network interface card uses 1 and 2 for transmitting and the PC uses 1 and 2 for receiving. And similarly, the network interface card uses 3 and 6 pins, the number of pins I mean, for receiving, and the switch uses 3 and 6 for transmitting. That's why we use straight through cabling to connect one here to one here, and two here to two here, and three here to three here, and six here to six here, which will be a straight through cable. There is another type of cable pin out which called crossover cable. If the two devices send and receive on the same pins, you use crossover cabling. And for these two connectors on both ends of the cable, this is side A and this is side B, you connect 1 and 2 to 3 and 6. And here we started with the orange, the striped orange, and the solid orange. So the striped orange to 1 here to 3 here, and 2 here to 6 here, and 3 here to 1, and 6 here to 2. This is called crossover cable, as you can see here. 1 to 3, 2 to 6, 3 to 1, 6 to 2. This, in case of the two devices, uses the same pins for transmitting and receiving. So if you are going to connect switch to switch, this is the symbol of the switch. You will use crossover cable. If you are going to connect a PC to a PC, you will use crossover cable. If you will connect a PC to a switch, you will use straight through cable. And this figure summarizes the type of cable pin out. If you are going to connect PCs to each other, use crossover. If you are going to connect routers to each other, use crossover. Or PC to a router, use crossover. If you are going to connect a PC to wireless access point, use straight through, but that's why I made it in black color. But if you are going to connect a PC to a switch, use a straight through cable. router to switch, straight through router, and PC uses 1 and 2 for transmitting and 3 and 6 for receiving. So this figure, if you are going in the right hand side, if you are going to connect two switches, use crossover cable. But PC to switch straight through, router to switch straight through, access point to switch straight through. That was for 10 megabit per second and 100 megabit per second. So what about the cabling pin outs for 1 gigabit per second base T or 1000 base T? As we mentioned, this is the speed, 1 gigabit per second, and this T for UTP or STP cabling. What will be the UTP STP cabling pin outs for this standard? It will use the 8 pins or the 8 cables. You have to connect for a straight through 1 to 1, 2 to 2, 3 to 3, and so on. If you will start with green, with green, it will be standard TIA EIA 568A. If you will start with orange, it will be TIA EIA 568B. But you have to connect all the 8 wires. This is for the straight through cables. For crossover, you will connect 1 here to 3, 2 here to 6, 3 here to 1, 6 here to 2, and similarly 4 here to 7, 5 here to 8, 7 here to 4, 8 here to 5. This is for crossover cable for 1000 base T. So now we finished the copper wires. What about the fiber optic cabling? Let's discuss fiber cabling transmission concepts. Actually, fiber optic cabling uses glass as the medium through which light passes, varying that light over time to include zeros and ones. This variation in the light, whether it's on or off means 0, on means 1. So we have here a fiber glass and a source of light. So light can go inside the fiberglass. Fiber optic cables uses fiberglass, which allows a manufacturer to spin a long, thin string of flexible glass. Fiber optic cable holds the fiber in the middle of the cable, allowing the light to pass through the glass. Because there are layers when we are using a fiber optic cable that we will demonstrate in the next slide, which is very important attribute for the purposes of sending data. So the fiber optic cable that holds the fiber in the middle of the cable allows light to pass through the glass. And this is the most important attribute for sending data. Also, sending data through a glass fiber works well. The glass fiber by itself needs some help or some protection because the glass could break. So the glass fiber needs some protection and strengthening because the glass fiber is very thin. It can be broken. That's why in this slide we show how to protect this glass fiber, or we call core, and it has cladding around it to do full internal reflection in case of light inside the core. And there is a buffer here for protection, strengthener for protection, and an outer jacket for the cable. These are the components of a fiber optic cable. Light is going through this core, and this core can be broken. So that's why you are strengthening it with outer jacket, strengthener, and buffer. So let's discuss the fiber cabling transmission concepts. For fiber optic, we have multi-mode fiber and single-mode fiber. The difference is that the multi-mode fiber uses a source of light LED or light emitting diode, where the transmission of light can be reflected inside the core. And there is a formula for how the light will have a total internal reflection, but we are not going to deep dive inside this. You just have to know that the light is going to be reflected inside the core until going to the other side. But for single mode fiber, we use a laser source of light where the beam can goes inside the core to the other side. So for fiber, we have single mode and multi-mode. Single mode uses laser as a source of light. Multi-mode uses LED as a source of light. And for multi-mode, we have a total internal reflection inside the core. So to transmit between two devices, you need two cables, one for each direction. We have here transmitting port and receiving port. We use two cables, one connected here for transmitting and the other side for receiving, and one side here for receiving and the other side for transmitting. If you will connect two cables in two both ends and the link will not goes up, then reverse the cabling, because they may be transmitter here for transmitting here and receiving here for receiving here. So let's discuss the fiber cables connector types. As we mentioned, for UTP and STP cabling, we have only one connector, which is RJ45. But for fiber cables, we use multiple connectors, 3 to the single mode and 2 to the multi-mode. So for the single mode, we have LC connector, SC connector, and FC connector. They all end with the C letter. And as you can see here, the shape of the cable, the connector, this is LC connector. And we use two cables, one for transmitting and one for receiving. And this is how the SC connector look like. And for the FC connector, this is how it looks like. For multi-mode, we have ST connector and MTRJ, and this is how they look like. This is the MTRJ. So using fiber with Ethernet, you need a switch with either built-in ports that support a particular optical Ethernet standard, or a switch with modular ports that allow you to change the Ethernet standard used on the port. These modular ports can be with connectors LC or SC or FC or whatever. You can change based on what you want. Refer back to figure 2.8, which shows a photo of a switch with two SFP ports into which you could insert any of the supported SFP plus modules. Those SFP plus ports support a variety of 10 gigabit per second standards like those listed in the next table. So for a standard 10 gigabase S, you use multi-mode cable and the maximum distance is 400 meters. For a standard 10 gigabase LX4, you use multi-mode fiber with maximum distance 30 meters. With 10 gigabase LR, single mode, the cable type, and the maximum distance is 10 kilometers per second. Sorry, 10 kilometer, the distance. And for 10 gigabase E, single mode, the maximum distance is 30 kilometer. So those SFP plus ports support a variety of 10 gigabit per second standards like those listed in this table. Then, now we finished discussing the physical layer of the TCP/IP. Now let's move to the Ethernet data link protocols, which is layer 2. There are several protocols and rules that Ethernet uses regardless of the type of the link. The Ethernet data link protocol defines the Ethernet frame, as we mentioned in encapsulation in the first video of chapter 1, that the Ethernet uses the concept of frame, where data is coming from the upper side, the upper layer, the layer 3 to layer 2, and then the encapsulation encapsulate a header and trailer. So the Ethernet frame has an Ethernet header at the front, the encapsulated data in the middle, and an Ethernet trailer at the end. And those are the fields of an Ethernet frame: preamble, start of frame delimiter, destination MAC, source MAC, type, and the data. And here the trailer is frame check sequence. So let's give a description of each field of this frame. The preamble is used for synchronization, and it has 7 bytes. The start frame delimiter, or SFD, is 1 byte field, and it signifies that the next byte begins the destination MAC address field. It tells just as after the synchronization, it just signifies that the next is the destination MAC address. So what is the destination MAC address? It's first of all, it's 6 bytes field, or 6 bytes long, and it identifies the intended recipient of this frame. And the source MAC address is also 6 bytes. It identifies the sender of this frame. The type is 2 bytes, and it defines the type of protocol inside the frame, inside the data field, which is an IPv4 or IPv6. The data embed from the upper layer maximum should be 1500 bytes, and it holds the data from the higher layer. The sender adds padding to meet the minimum length requirement for this field. And the last trailer, the trailer frame check sequence, it is 4 bytes. It provides a method for the receiving network interface card to determine whether the frame experienced transmission error. Actually, in the coming slides, we will take each field of these and we will demonstrate it in more details. So for Ethernet addressing, the source and destination Ethernet address fields play a huge role in how Ethernet LAN works. The sending node puts its own address in the source address field, and the intended Ethernet destination device's address in the destination address field. So if a PC here, PC1 and PC2, this has a MAC address A, for example, and this has a MAC address B. If PC1 is communicating with PC2, The frame will have source MAC address A and destination MAC address B. And later on, we will demonstrate what are the MAC address and how many bits in this slide actually, and the coming slides. So the sender transmits the frame, expecting that the Ethernet LAN as a whole will deliver the frame to the correct destination. And Ethernet addresses are called Media Access Control Addresses or MAC addresses. These MAC addresses are 6 byte long or 48 bits because the byte has 8 bits, and it is 48 bits binary numbers or 6 byte binary numbers. But for convenience, most computers list MAC addresses as 12-digit hexadecimal numbers. So if we will say here we have 1 byte, second, third, fourth, 1, 2, 3, 4, 5, 6 bytes, we will have 48 bits, and these 48 bits will be represented in 12 hexadecimal digits. As you see here, for example, Cisco represents the MAC address as this, looks like this: 12 digits, 4 on each group, 4 digits here, 4 digits here, separated by a dot, and 4 digits here. This is how the MAC address is represented on Cisco switches and routers, mainly Cisco switches. And for Microsoft operating systems, it represents the MAC address in this format. They are both 12-digit hexadecimal, but how they are represented based on the vendor. So most MAC addresses represent a single network interface card or an Ethernet port. So these addresses are often called a unicast Ethernet address, and the meaning of unicast is one host sending to one destination. So unicast refers to that the address represents one host or one interface. There are different types of addresses that we will demonstrate in the coming slides. There is multicast address and broadcast address. But for a unicast, it refers to one host or one interface. Before a manufacturer can build Ethernet products, it must ask the IEEE to assign the manufacturer a universally unique 3-byte code. This code is called the organizationally unique identifier. As we mentioned in the previous slide, the MAC address consists of 6 bytes. The first 3 bytes are called organizationally unique identifier, and the last 3 bytes are called vendor assigned because they are assigned by the vendor. So when a manufacturer builds a specific Ethernet product, it must ask the IEEE to assign it the first 3 bytes, which is called OUI. Then the manufacturer assign the devices, the Ethernet products, another 3 bytes that is called vendor assigned. As we mentioned here, where is the mouse? Yes. The manufacturer also assigns a unique value for the last 3 bytes, which is called vendor assigned bytes. And this is to make the MAC addresses unique, so no device in the world has the same MAC address as another one. Each Ethernet product has a MAC address. For example, if a network interface card, it has a MAC address that is unique from all other network interface card. And as a result, the MAC address of every device in the universe is unique. As you can see here, the first 3 bytes are called OUI, and the last 3 bytes are called vendor assigned. And OUI is 24 bits, and vendor assigned is 24 bits. And they are represented in 12 hexadecimal digits. 6 for OUI and 6 for vendor assigned. That's why you can find some network interface cards or net switch ports whose MAC address has the same 6 hexadecimal digits because they are coming from a specific vendor. But the last 6 digits should be unique for each device. So Ethernet addresses go by many names. We can call it LAN addresses or Ethernet address or hardware address, burnet-in address, physical address, universal address, or MAC address. If you will use Microsoft, for example, to show the MAC address, it will call it physical address. If you will check the Cisco products, it will call it MAC address. Sometimes other vendors call it burnet-in address or BIA. So in addition to unicast addresses that represents only one host or interface, Ethernet also uses group addresses. And group addresses identify more than one LAN interface card. So some network interface cards can be in a group, and this group has a group address. So a frame sent to a group address might be delivered to a small set of devices on the LAN, or even to all devices on the LAN. So the IEEE defines 2 general categories of group addresses for Ethernet: broadcast address and multicast addresses. For broadcast, the MAC address value will be full F hexadecimal digits. The 12 hexadecimal digits are F, and this represents a broadcast address. So frames sent to this address should be delivered to all devices on the Ethernet LAN, and it has this value. In case of multicast addresses, frames sent to a multicast Ethernet address will be forwarded to a subset of the devices on the LAN, not all, not as the broadcast address, that volunteers to receive frames sent to a specific multicast address. So we have unicast address, broadcast address, and multicast addresses. Unicast is sent to one device or interface. Broadcast to all devices on the Ethernet LAN. Multicast to a subset or a group of devices on the LAN. Then let's go to the Ethernet type field in the Ethernet frame. The type field identifies the type of network layer 3 packet that sits inside the Ethernet frame. So we have 2 types, either IPv4 or IPv6. If it's an IPv4, the type value will be 0800. If it is an IPv6 address, the type field will be 86DD, because Now, today, the most common network layer protocols are both from TCP/UDP are IPv4 and IPv6. The old IP systems network architecture used a different value, but recently we use only either IPv4 or IPv6. So Ethernet also defines a way for hosts or nodes to find out whether a frame's bits changed while crossing while crossing over an Ethernet link. As we mentioned, there is a field called FCS or frame check sequence, and it is used in error detection, and its location is in the Ethernet trailer. Think about it like that. When you receive a stream of bits and they have a field called FCS, and this FCS comes from a mathematical operation on the stream of bits. You do a specific mathematical formula, and then you get this FCS, and you attach this FCS to the frame in the frame trailer or Ethernet trailer. Once the receiver receives this stream of bits, it will do the same exact mathematical formula to the bits and get a new frame check sequence. And then it will compare the resulted frame check sequence to the frame check sequence came with the stream of bits. If they are equal, then the stream of bits has no errors. If they are not equal, then there is an error and the frame will be discarded. So the Ethernet frame check sequence field in the Ethernet trailer, the only field in the Ethernet trailer, gives the receiving node a way to compare results with the sender to discover whether errors occurred in the frame. As we mentioned, the sender applies a complex mathematical formula to the frame before sending it, storing the result of the formula in the FCS field. Then the receiver applies the same mathematical formula to the received frame. Then the receiver compares its own results with the sender's results. If the results are the same, the frame didn't change. It means it is error-free. Otherwise, the frame has error and the receiver discards the frame. Here is a note that the error detection does not also mean error recovery. Error recovery means I will recover the error from the errored bits, and then I will make it error-free. But error detection doesn't mean that. It means that I will detect there is an error. If there is an error, the receiver will discard the frame. So Ethernet defines that the errored frame should be discarded. But Ethernet doesn't attempt to recover the lost frame. Other protocols, notably TCP in layer number 4, recover the lost data by noticing that it is lost and sending the data again. It tells the sender, please send that lost frame again. So here we will discuss sending Ethernet frames with switches and hubs. Basically, the use of modern switches allows the use of full duplex logic, which is much faster and simpler than half duplex logic, which is required when using hubs. When you think about half duplex, it comes to your mind hubs only, because switches uses full duplex. What is the meaning of half duplex and full duplex? Half duplex means that the device must wait to send if it is currently receiving a frame. So in other words, it cannot send and receive at the same time. This is the definition of half duplex. The device cannot send and receive at the same time, either send or receive. But full duplex, the device does not have to wait before sending. It can send and receive at the same time. Here it shows an example of sending data in a modern Ethernet LAN. Where PC1 here in step number 1 encapsulate an Ethernet frame. This is the header and this is the trailer, and it mentions PC1 as the MAC address, the sending MAC address or the sender MAC address, and PC2 as the destination MAC address. And as we mentioned, the MAC address is 12 hex digit numbers. So the PC1 encapsulates the frame with the sender and receive and destination MAC addresses and send to switch 1. And the link is full duplex because he can send and receive at the same time. Because modern switches supports, of course, uses full duplex concept. So switch 1 will decide that it should forward the frame out of interface Giga 01 and send to switch 2 because it checked the destination MAC address inside the Ethernet header. Now switch 2 will do the same and check the destination MAC address and decide that the destination MAC address is connected on port fast 002, and it will send the frame out of this port, this time to BC2. So, as we mentioned, using half duplex with only LAN hubs. To understand the need for half duplex logic in some cases, you have to understand a little about an older type of networking device called a LAN hub. Actually, it is very seldom that you will find LAN hubs in recent networks. When the IEEE first introduced 10 base T in 1990, Ethernet switches didn't exist yet. Instead, networks used a device called a LAN hub. So before switches, we had these types of LAN hubs. And LAN hub actually is a layer 1 device. It works only on the physical layer. So here, like a switch, a LAN hub provided a number of RJ45 ports. You can find a LAN hub like this, 45 port, RJ45 ports. And we have here 4 ports. This is hub. As a place to connect links to PCs. However, hubs use different rules for forwarding data. So to define LAN hubs, it forwards data using physical layer standards rather than data link standards. This is the major difference between switches and hubs. Hubs uses physical layer standards or forward data using physical layer standards, but switches forward data using the data link standards. And LAN hubs are considered to be a layer 1 devices. Here we give an example when an electrical signal comes in one hub port, the hub repeats that electrical signal out all other ports except the incoming port. If someone is sending through this port, the hub will repeats all the signal out of all ports except the incoming port, which is not logic. By doing so, the data reaches all the rest of the nodes connected to the hub, so the data hopefully reaches the correct destination. So the hub has no concept of Ethernet frames of addresses, making decision based on those addresses. It has no concept of frames or addresses or making decision based on these addresses. The downside of using LAN hubs is that if 2 or more devices transmitted the signal at the same instant, the electrical signal collides and becomes garbled. The hub repeats all received electrical signals, even if it receives multiple signals at the same time. This is the concept of the hub. It repeats all the received electrical signals. Let's give an example here. This PC sent an electrical signal, and at the same time this PC sent an electrical signal. The hub will send this out of this and out of this, and 1B will be sent out of here and here. So what you can think here will occur? Of course, collision will occur in this, and Larry will receive a garbled data. So for completeness, note that the hub floats each frame out all other ports except the incoming port. So in the example, Archie's frame goes to both Larry and Bob. Bob's frame goes to Larry and Archie. So to prevent these collisions with hubs, the Ethernet nodes must use hub duplex logic to either send or receive at a time instead of full duplex logic. So if you replace the hub in figure 223 with the LAN switch, the previous figure, you will replace this device with switch. The switch prevents the collision on the left. Why? Because it uses the concept of full duplex, specific link for sending and specific link for receiving. As you can see here, the switch operates as a layer 2 device, but the hub is a layer 1 device based on the working layer, the data link layer, meaning that it looks at the data link header and trailer. So a switch would look at the MAC addresses, and even if the switch needed to forward both frames to Larry on the left, the switch would send one frame and queue the other frame to avoid this collision until the first frame was finished and being sent. This will prevent the concept of collision using Ethernet switches. But with layer 1 hubs, it cannot prevent this collision unless you use a concept called CSMA CD. And here, nodes that use half duplex logic actually use a relatively well-known algorithm called carrier sense multiple access with collision detection, or CSMA CD. The nodes must use this algorithm. The algorithm takes care of the obvious cases, but also the cases caused by the unfortunate timing. Unfortunate timing when two signals are sent at the same time. For example, two nodes could check for an incoming frame at the exact same instant. Both realize that no other nodes is sending, and both send their frames at the same exact instant, causing a collision. So CSMA CD covers these cases as well, as follows. This is how CSMA CD works on nodes. Step 1, a device with a frame to send listens until the Ethernet is not busy. Once it is not busy, when the Ethernet is not busy, the sender begins sending the frame. If it is busy, it should wait for a specific amount of time. If it is not busy, the sender can send the frame. Step 3, the sender listens while sending to discover whether a collision occurs. Collisions might be caused by many reasons, including unfortunate timing. So what will happen if a collision occurs? All currently sending nodes do the following. They send a jamming signal. Hey, there is a collision occurred. That tells all nodes that a collision happened. Then they independently choose a random time. So each one will choose a different, hopefully, each node will choose a different random time to wait before trying again to avoid unfortunate timing. The next attempt starts again at step 1, and step 1 was to listen until the Ethernet is not busy. Also, most modern LANs don't often use hubs, and this is a fact, and therefore don't need to use hub duplex. Enough old hubs still exist in enterprise networks, so that you need to be ready to understand duplex issues. If, for example, you have a network like that, a PC connected to switch 1 and switch 1 connected to switch 2, and switch 2 has two interfaces, one to PCB and the other port, another port for hub. If you will use hub, then you must use this port in half duplex mode, and the other ports in full duplex mode. Just here because you are using hub. So each network interface card and switch port has a duplex setting. You can adjust this setting from the switch configuration, and we will know later how to configure the duplex setting when we discuss the command line interface of Cisco interface. So for all links between PCs and switches or between switches, use full duplex. However, for any link connected to a LAN hub, then the connected LAN switch and the network interface card port should use half duplex. As you can see here, the PC uses half duplex and the switch uses half duplex because they are connected to a hub. And to this, we come to an end to this video. I hope it's been informative, and thanks for watching.